Okay, welcome back. Here's our teacher of the day, Salman Khan from Khan Academy. So you can visualize him. Although it's hard for me to visualize him when I think of him looking just like Ray Barone from Everybody Loves Ray, TV series from about 10 to 15 years ago. Hi, Ray. Alright, so this video is about, as the British say, nomenclature. How to name the compounds from their formulas. Of course, you also have to be able to take the formula and come up with their name. So I'm just going to review the notes first, and then I'll come back to all the goodies that I stole off the internet. Let's see what we got. Hey. There we go. Get my free update. Got to do that. I'm an old person. I like free stuff. All right, naming compounds. First of all, you have to understand there's 14 million different compounds, and the system for naming them can be complex if the material itself is very complex. But we're going to focus on what's called binary compounds. Now, binary usually means two different elements, but in this case, it could also mean a polyatomic group. So binary meaning you have two components. There's a positive component, and then there's a negative component, but technically the definition to mesmerize is two different elements. Okay. And we're going to use a combination of systems, but the most important is what's called the IUPAC system. It's the International Union of Pure and Applied Chemists, or chemistry rather, and you don't have to know that. Just know that there's a whole bunch of people who come together each year and try to come up with a system for naming things, and they meet different places throughout the world once a year. They're last couple of years they've been meeting in Brazil, but I'm going to guess based upon the COVID outbreak in Brazil that they probably won't be meeting there this year. In the IUPAC system, here's what IUPAC says. IUPAC says any naming system is actually okay as long as it distinguishes one material from another material. In other words, you can make up your own naming system if you want, and as long as it distinguishes one thing from another, it's okay. However, it's not done that way, and when you go to the higher level chemistries, they're going to expect that you know the actual naming systems. So we're going to start with binary ionic compounds. Again, to be able to name these, you have to decide whether you're dealing with an ionic compound or a covalent compound. In the next video, we're going to talk about acids, which have their own little naming system, and hydrocarbons, which are used as fuels in the lab, and they have their own little naming system as well. We'll start with ionic compounds. Here's the definition. Involves the bonding of a metal with non-metal, or could be a metal or a non-metal with another polyatomic group, or it could be two polyatomic groups. Again, one thing positive, one thing negative. And it has a slightly different naming system, but it is very slightly different than covalent compounds, which involve the bonding of two or more metals. So being able to identify the difference between ionic and covalent, I would say memorize the definition of ionic or covalent, and then everything else that we're doing in this chapter is ionic. And then when we talk about bonding mechanisms later in the course, then you'll be more important to make a distinction. So how do you decide whether a compound is ionic or covalent? So we're going to go back to our little periodic table that we had. Here we go. And we said that when we look at the materials, the positive thing is going to be on the left side, and the negative thing is going to be on the right side. Notice with the charges, that's how the periodic table is set up as well. Positive charges on the left side, negative charges on the right side. So our metals are on the left of that break line, and our nonmetals are to the right of that break line. And actually, some of the materials touching the break line are metalloids, but we're not going to worry about those for now. All right, naming system for ionic. Now, do understand, IUPAC meets and they keep changing these rules as they discover more proteins and DNA and RNA sequencing and things of that nature. It gets more and more complex, so they keep changing the rules. So this is based on a set of rules from 1994. There was an update in 2007. There was a big update in 2014, but ionic hasn't changed since prior to 1994. So we're going to go with that, what's called the stock system, they used to call it, and now it's the IUPAC ionic system. First element keeps its regular name. So it doesn't matter how many sodiums are in your compound. It's just called sodium. And if there's 3 strontiums on the left side of your compound, it's still called strontium. There's no distinction between how many you have and the material you have, because in an ionic compound, there's only one combination you can get from reacting a metal with a non-metal. So there's no need to make a distinction. Like, for instance, you were taught CO2 is carbon dioxide. Well, yeah, you have to make a distinction there because there's a couple of compounds that have carbon and oxygen in it. CO is carbon monoxide. So we have to make a distinction between the two. But with sodium chloride, there's only one compound where you take sodium and attach it to chlorine, and that's NaCl. So we're not going to call this monosodium monochloride. It's just sodium chloride. So the first thing, regardless of how many you have, keeps its regular name. So if we had this compound, doesn't matter how many aluminums we have, doesn't matter how many oxygens we have, we're going to call it aluminum, not dialuminum, aluminum oxide, not trioxide. This is actually a very easy naming system. The first element, the positive charged element, keeps its regular name, and the negative charge element, you take the name, cut out its ending, put in "ide." So oxygen becomes oxide, sulfur becomes sulfide, bromine becomes bromide, phosphorus becomes phosphide. And I'll laugh if you're at home and you actually answered that because I paused. When you have a polyatomic group, doesn't matter how many atoms are in that group, they just keep their regular group name. So if you have ammonium, NH4, and let's say we need 2 of them to connect to sulfur, this is not called diammonium, it's just called ammonium. And then sulfur becomes sulfide. Now, if the polyatomic group is at the end, it still keeps its regular name. So the positive thing is calcium. The negative thing is the carbonate group. So we're just going to call this calcium carbonate. Now, when I put a circle around that positive and negative, I'm not saying how much charge they have there. I'm just saying that's the type of charge they have. For instance, in calcium carbonate, the calcium actually has a 2+ charge and the carbonate has a 2- charge. In our example with ammonium and sulfide, ammonium has a +1 charge, sulfur has a -2 charge. Notice the charges are not part of the formula. The charges are used to derive the formula. Notice they're not part of the name. Okay, those are pretty easy. However, if we have a transition element, because transition elements can have multiple oxidation states, we need to put the oxidation state in parentheses with Roman numerals next to it. So, for instance, if we had this compound, then let's say we have NiCl3. We look up Ni, that's nickel, and Cl3. We're not going to write trichloride, it's ionic, so we're just going to write chloride. But I left a little space because we need to figure out the charge on the nickel. Now, how do you do that? I'm glad you asked. Let's do that over here. We have nickel chloride. Now, we said the transition metal nickel could have multiple states. However, chlorine is always -1. So we know that. Chlorine's -1, and there's 3 chlorines, so that totals up to be a -3. So to balance this, what must nickel be? It has to be +3. So we would write in Roman numeral 3, nickel 3 chloride. And we're going to practice these. That's why I'm going through it pretty quick. Now with covalent, all you do is treat the non-metal on the left the same as you would a transition metal. For instance, you were taught that, let's do this one, N2O5, that's dinitrogen pentaoxide. And that's the old naming system, and that's fine. There's still people using the old naming system. Sometimes you actually have to use the old naming system, but in the IUPAC, here's how they would come up with the name. They would say, look, oxygen is -2, and there's 5 of them. So that means the negatives come out to be -10. That means that the positives have to come out to be +10. So the name of this compound is nitrogen 5 oxide. How did I get the 5? Well, because there's two nitrogens in the formula, and they share that positive 10. So do 10 divided by 2, and you get that each nitrogen actually has a charge of positive 5. So it's nitrogen 5 oxide. They don't want the total charge. Positive 10 is the total charge. When you put it in the name, they want the oxidation state on each individual nitrogen, which is positive 5. So we call this nitrogen 5 oxide. And that's all there is to it. Done. And this explains how to do it, how I did it. What I did was I started with the negative thing, which kept its normal oxidation number. And then I took the positive thing and I did a little bit of mental algebra to get the charge on the first element. Same thing with transition numbers. And then our last set of rules has to do with the old names that you learned in middle school. So we still use those, so you're welcome to use them. They are the ones where instead of oxidation numbers, we're going to use the prefixes to say how many of each atom you have. Remember, this is only for covalent compounds. So if we had something like, I don't know, I'm going to make something up. I know the charge is off on this, but we'll just use it for an example. S2O3. So we would say, how many sulfurs are there? 2. So we're going to use the term di. Disulfur, because the first element keeps its normal name. And then we're going to call the last element trioxide, because there's 3 oxygens, and we change oxygen to ide. The second one gets changed to ide. So disulfur trioxide. And then we'll come back to these in the next video. Okay. So let's review real quick before we start practicing this, because really the reason why I went through it so fast is because it's the sort of thing where you really have to get in there and practice it. So let's see what they did here. They had a compound, CaCl2. And the first thing they did was they broke up the cation, which is a name for a positive ion, and the anion, which is the name of the negative ion. So the positive thing was calcium, and the negative thing was chlorine, but they changed chlorine to chloride. So then you look at the compound and you say, all right, is this covalent? 2 nonmetals? No. Is this a transition metal? Well, calcium is found in group 2, so it's a main group metal. So that means we do not need parentheses. In fact, if you put in parentheses, it's actually technically considered wrong. So we're just going to call it calcium chloride. Notice they did not call it calcium dichloride. With the second one, and this is the example I used in the last video. I didn't know before. I should have stole this stuff in advance, I guess. All right, what's the positive thingy in that formula? Copper. What's the negative thing? Oxygen. So we changed oxygen to oxide, and then we just have to go back and we have to figure out how they came up with this Roman numeral 1. Well, that's not hard to do. Again, what's the charge on oxygen? Always group 16, -2. So that means that all of the coppers have to add up to be +2, and there's 2 of them, so each copper is actually +1. Total charge +2, but each copper is +1. So they're going to call this copper 1 oxide. Again, pretty easy. Here's the even easier ones. Wow, the internet is a treasure trove of things to steal. If they give you the ions, Na plus Cl minus, we know that that combines to make NaCl. So now we have to name it. Sodium's group 1, main group. Chlorine, group 17, main group. So this has a regular ionic name, sodium chloride. Same thing with this second example. Magnesium's in group 2, main group, so it keeps the name magnesium. However, OH minus is one of those special polyatomic groups, so we're going to just call that hydroxide. Remember, the group keeps its group name. OH is hydroxide. And we need 2 of those hydroxides to balance out the charge on the magnesium. So our formula is MgOH2 and the name magnesium hydroxide, not magnesium dihydroxide. That would be for old school covalent. All right, so what if we had 2 polyatomic ions? Well, that makes it even easier, because the rule for the polyatomic ions is that they just keep their regular name. So we'll take a look at this, right? This is the compound right here, and we got a polyatomic group called ammonium, and we have a second polyatomic group called sulfate. So the name is just down here, ammonium sulfate. Again, not hard. Let's take a look at the IUPAC for covalent. Carbon 4 iodide. How would we come up with the formula? Because you got to do that too. You can't just look at the formula and come up with a name. We're also required to teach you how to do the opposite. Take the name and come up with the formula. Well, if they give me the name, that's pretty easy to figure out here. Carbon 4, they told me the charge. It's carbon with a positive 4. Iodine is in group 17, so I'm going to look it up. -1 charge on my little periodic table. So I need 4 iodines to balance the charge on the chloride. Second one, sulfur, Roman numeral 6. So this is S with a 6+ charge. Oxygen is O, group 16. So it always has -2. It doesn't always have -2, by the way. There are peroxides, which is a special polyatomic group which each oxygen only has a -1 charge. And there's actually something called superoxide where each oxygen only has a -1/2 charge, but there are exceptions to the rule. The rule is oxygen has a -2 charge. So we're going to need 3 of these oxygens to balance out the 1 sulfur, so we get SO3. Without looking at the answers, I know you saw them. You should probably pause here and try the last 3, cover up that answer, and do the best you can, justify the charges and see how it works out. And I know it's impossible to unsee the answers, and then I will come back and finish off explaining the rest. Hey, I'm back. All right, so nitrogen, IV, so that's N with a 4+ charge, and oxygen has -2 charge, so I need 2 oxygens to balance out that nitrogen, so the formula must be NO2. Arsenic 3. So look up arsenic. Notice it's not AR. AR is argon. It's AS. So we're going to put a +3 outside of that because it's a 3+ charge. Sulfur becomes sulfide. Group 16, -2 charge. And then we do our little crisscross method on this one. Multiply by 2 on the arsenic, multiply by 3 on the sulfide, so that they both wind up with a charge of 6. And we wind up with 2 arsenics and 3 sulfurs. And then the last one, phosphorus with a +3, fluorine with a -1, and that means we're going to have to take fluorine and multiply it by 3. So we get PF3. Right? Again, pretty easy. Don't fight it. It's not hard, but it is going to take practice. And it's going to take practice because we're not going to tell you which compounds are ionic, which ones are covalent, which ones are transition metals. You have to practice, and we're going to mix them all up. So there are some practice tests that I posted on the website for you. All right, old school covalent, that carbon dioxide, carbon monoxide stuff. Okay, if you're going to use the old school covalent, then you have to know your prefixes for each of the atoms. Now, they don't use mono on the first atom. Like CO is carbon monoxide, or you can say monooxide. I actually looked it up. They accept each one. So if you want to write monoxide, MONOXIDE, that's fine. If you want to write monooxide, MONOOXIDE, that's also acceptable. But they don't use mono on the first element. I don't really know why. Have never looked it up, never cared enough. 2 is di, not bi. 3 is tri. 4 is tetra. And then the rest are sort of like geometry. 5 for penta, 6 for hexa, 7 for hepta, 8 for octa, non for 9, nona, and deca for 10. I'm going to ask you to go up to 11 and 12. If there's 11 of an atom, we're going to use the term undeca. And if there's 12, we're going to use the term dodeca. Now, if there was 13, we would call it trideca. 14 would be tetradeca, 15 pentadeca, 16 hexadeca. And when you get to 20, it's of course called icos for some reason. So if you had 21, it would be unicos, and 22 would be doicos, and 30 would be tricos, 40 would be tetros, 50 would be pentos, 60 would be hexos, and 90 would be nonos. 100, however, is kilya. I don't know why. There's a compound called kilyasane with 100 carbons in it. I have no idea why it's not decos, but it is kilya once you get to 100. But anyway, you only have to know up to the first 12. So suppose we're using old school and we have this compound. Again, I'm making stuff up. I'm not seeing whether or not the Lewis structure is matched to see if the compound exists because I'm in a hurry here. All right, so we use the old school system and we say, all right, covalent. Phosphorus is nonmetal. Oxygen is nonmetal. So I just can say, I don't feel like using IUPAC, Mr. Burnett. You said we could use IUPAC. I got ahead of myself here. IUPAC or old school. So stuff that you learned in middle school still counts. Diphosphorus, 4 is tetra. So we call this tetra oxide. What if you had this? Okay, so you pause here and you can try it. Hey, welcome back. So we look up Xe, that's xenon. Notice I didn't write monoxenon. We don't use mono on the first element. And then 6 for fluorine, so this would be hexafluoride. Let's try one more and then we will move on with our lives. Okay, try that one. Ce2N. Actually, let's not do that one because that one acts like a non-metal, but it's not actually a non-metal. Let's try something else here. Let's mess this thing up and do a little, I don't know, make something up here. Ge2N. Go ahead and try that one. All right, I'm back. So we look up Ge, that is germanium, and there's 2 of them. So we're going to write di-germanium, and then N is for nitrogen. So we're going to write mono. Notice I use mono because it's the second element. Mono nitride. All right, I'd like you to go back and try these 3 using the old. Well, you can't on this one. No, only this one. Let's do this one using the IUPAC system instead. Instead of xenon hexafluoride, what would it be in the IUPAC system? I'll pause and wait. Hey, I'm back. Okay. So the first one is xenon, and the second element is fluorine. So it's going to be xenon fluoride, but we have to figure out the charges. Now, fluorine is normally -1, but there's 6 fluorides, so its total charge is -6, which means the xenon has to be +6. So in the new IUPAC, this would be xenon 6 fluoride. Okay. Again, not difficult. And then the last thing, common names. Some things have their own special names, and we can continue to use them. Like H2O, nobody calls this dihydrogen monoxide. Nobody calls it hydrogen 1 oxide. Nobody calls it hydroxyodic acid. Everybody calls it water. And NH3, nobody calls it nickel 3 or nitrogen 3 hydride. It's called ammonia. Carbon dioxide solid is called dry ice. NaCl is called table salt. But these are the big 2 here, ammonia and water, as far as the common names go. All right, so I'm going to let them practice with you in the recitation. And you're going to do, of course, practice problems on the practice test and the recommended problems that I posted for the chapter. And we got one more video, how to name acids and how to name hydrocarbon stems. And we will be done with the first unit.